Okay, hi everyone. Well, this morning, this afternoon, whatever time it is for you, we have a slightly different thing we're looking at. We are looking at Jonathan Gorad's work on a system for using our Wolfram model physics project ideas to make a gravitation, general relativity simulation solving system. And that's okay. Over to Jonathan, maybe who will now deny that my description is correct.
No, I think that's a perfectly reasonable description. But I think it's important to distinguish a few different objectives with this framework. So the first is that, okay, the first is a very pragmatic thing, which is that in general, numerical GR simulations are quite hard to set up if you're not, if you're a sort of standard user. So the usual workflow is, because, okay, to backtrack for a second, for any practical numerical relativity simulation, you're going to have a lot of equations, and they're going to be pretty complicated. And if you're simulating, general relativistic magnetohydrodynamics, plasma flow onto a spinning black hole or something, you could easily have 100 plus sort of partial differential equations that you have to solve. So no one's going to implement that by hand. So the standard workflow has now become that you write the equations in some kind of abstract notation in Wolfram language or a similar system. And then you run some package that then does automatic code generation from that. So there's probably the most widely used package is this Wolfram language package called Crank, which does this, where you enter essentially a tensor equation in Einstein notation, and it goes away and it synthesizes C code, which you can then plug. Oh, usually it's C code, sometimes it's Fortran or something, which you can then plug into Cactus or Whiskey or GR Chombo or whatever other numerical relativity code. Then you go run that. It produces some data files. You then import the data files back into some other system. There's like packages like NRPy, which is a Python package that does the analysis and visualization and extracts event horizon information or gravitational wave data or whatever. So it's a slightly fiddly workflow. So the first objective with this is to make it so that you could do everything just within one notebook. So you can set up the initial data, set up all the coordinate systems, equip the space-time with matter fields, run the simulation, get the results back, visualize them, analyze them, etc., all within one instance. And then, as you say, Stephen, the other aspect to this is the Wolfram model aspect, which is the realization that when you're doing a numerical simulation with adaptive refinement, you are refining your grid structure based on certain information about usually based on projections of curvature tensors and things. And so then you have some rule that tells you when to refine, when to coarsen the mesh topology. And so in effect, what you're doing is you're defining a hypergraph rewriting system, but where the rewriting order is determined by the evolution of the PDEs. So it's really just a Wolfram model rule with some slightly odd event selection function. And then the other aspect of that is that you can then reconstruct certain information about the curvature from the topology. And so in fact, you reach a point where you can just throw away the information about the PDE system and you just have the pure hypergraph rewriting rule. And that's sort of that's how the numerical side of this works. But okay, so let me just, if I show, what's your favorite metric? These are the ones we currently support. Kerr? Okay, so if I say metric tensor Kerr, so say matrix representation, matrix form. Okay, so this is lower index, this is the ordinary metric tensor for the Kerr metric. We've got symbolic M, symbolic J for the mass and the quote unquote angular momentum parameter respectively. And this is in standard Boyer-Lindquist coordinates.
By the way, let me make a general comment here. I mean, in the world of PDEs, setting up the system is, that's been a huge roadblock in everything to do with PDEs. And we've been, it took us a couple of decades to have the kind of computational geometry capabilities necessary to, define multidimensional PDEs in a reasonable way. And, I think, yeah, it's interesting in this case because, the things that we've introduced in the last few years for sort of standard PDEs have been, Jonathan, I assume you've looked at this stuff, all the stuff to do with Dirichlet condition, et cetera, et cetera, et cetera. These kind of symbolic wrappers that represent different kind of.
Right. I have, although I don't. I mean, I don't claim to know that much about. I've looked at the documentation for them.
Yeah.
But I mean, as you're also probably aware, setting up initial data for the Einstein equations is even more difficult than it is in most PDE systems. Okay, actually, if we skip ahead to that just for a second, I mean, so the standard way we do that in Gravitas is we have this thing ADM decomposition, where so if I give that the Kerr geometry, there's an important like philosophical distinction here, right? There's metric. If I say metric tensor Kerr, that gives me the entire space-time metric as one kind of big blob.
Mm-hmm.
But for solving the Einstein equations numerically, that's not, you don't know that in general. You just have some initial data. And this is probably, sorry, I'm going to do something a little bit incomprehensible here, but I'll explain what I'm doing in a second. Let's say ADM, spatial metric tensor. So with ADM decomposition, what that allows you to do, okay, actually, let me start with a simpler ADM decomposition. Let's do Schwarzschild because that's diagonal. So here, what we're doing is we're saying, let's imagine we didn't know the space-time form of the Schwarzschild metric. Suppose we just had the data for an initial Cauchy surface, for an initial space-like hypersurface.
Mm-hmm.
So that would be this thing here, right?
Yep.
And then so what ADM decomposition says is, well, then show me symbolically what the space-time metric tensor would look like if I were to evolve the Einstein equations from that initial data. So if I say space-time metric tensor matrix form, okay, so we get this. And so this is, so here we see this 3x3 submatrix is the spatial metric, it's the initial spatial metric tensor. And in this stuff, you see a bunch of things related to alpha and beta. So alpha is this lapse function, beta is the shift vector. These are your gauge variables. These determine effectively your space-time coordinate system. So if you like, alpha tells you how you foliate the space-time, and beta tells you how you relabel the spatial coordinates as you move from one leaf of the foliation to another leaf of the foliation, right?
Let me just to make sure I understand this. So I mean,
yep.
That spatial metric tensor is on a space-like hypersurface. That's the way that you measure distances on that space-like hypersurface. Now you're saying, I see, I get what's going on. So you've got this foliated space-time going forwards in this ADM decomposition. And
right.
This is now telling you how to measure distances in that foliated world where the distances, where you have to measure sort of leaf to leaf or sheet to sheet distances. And
right.
that's determined by the alpha parameter is.
Right.
Okay.
And so then the point is that you can set up initial data for even for metrics where you don't know, or where there isn't an analytical solution for the whole space-time, right? So what ADM decomposition lets you do is, for instance, you can say evolution equations, and it will go away and it will grind for a second, and it will produce the complete PDE system for the ADM decomposition. So this is a system of coupled hyperbolic PDEs that evolves this initial data forwards in time relative to this foliation.
Okay, just so I'm clear, for flat space-time, that space-time metric tensor in the ADM decomposition is what? It's a time evolving. What does it look like? And is it
okay? So if we take
identity with an alpha and beta in the time coordinate.
So if we take a 3x3 Euclidean metric,
mm-hmm.
we use that as our initial space-like hypersurface. I'd say space-time metric tensor.
Okay, okay, hold on.
So in a sense, rather than defining distances, what this is doing, if you have two slices of the foliation, it's determining which point will correspond to which point in the next foliation, in the next
right.
slice of the foliation.
Right, exactly. So alpha is telling you the time-like distance between the between corresponding points on neighboring slices. Beta is telling you the space-like distance between the corresponding points.
Okay, I get it.
It's like the shear, right? So there is no obviously a connection, a vertical connection.
Right. Yeah. So which is here will
mm-hmm.
vary with time, so to speak.
Exactly.
Here varies with time.
Exactly.
Okay.
So okay, in this case here, we've not specified any gauge conditions, right? So alpha, beta are completely undetermined. But ADM decomposition, for instance, has a bunch of gauge conditions built in. So in the simplest case, we could say GD6 slicing condition, and that would just be alpha is identically 1. But we could also say, I've actually forgotten which coordinate conditions I've introduced now, but like I think we could do maximal slicing condition.
And what's the discovery interface for figuring out what conditions exist?
Well, it's probably more Jose's area than mine.
No, but I mean the discovery as in the system, in your gravitas system. What does it? How does it?
Oh, right. Okay. The point is, all of these can be these are all computations that can be characterized by just abstract tensor equations, right? So the maximal slicing condition is given just things like we have like things like minimal distortion conditions and so on. Those are all represented in terms of just tensor equations, actually for the extrinsic curvature tensor on the space-like hypersurface. Or typically in terms of the extrinsic curvature tensor. So all we're doing is we're taking those tensor equations, we're unrolling them, and possibly doing some simplification. So if we say reduced maximal slicing condition, it will do some simplification. There's code internally for keeping track of various algebraic identities and things that enable us to do canonicalization, although not very efficiently.
Jonathan, let me say one thing here. So the metric has freedom here, which is this gauge freedom, which corresponds to the alpha and beta. So the same metric can be re-expressed for different alpha and betas differently. Yeah. So that's why we have to impose some conditions that will find the metric in a given choice of alpha and beta. But in some situations, we have to solve for alpha and beta at the same time that we solve for the rest of the metric. So which is the slightly different scenario. So we are using PDEs like in NDSolve to have the metric predetermined and to impose conditions on a given geometry, say. So here we will be solving simultaneously for the metric and for the geometry.
Wait a minute. When you say solving for the geometry, you're describing that the ADM parameters, the alphas and betas. Is that what do you mean by solving for the geometry? Are you solving for the alphas and? I mean, alphas and betas have a lot of freedom. They have a lot of gauge freedom, but not
exactly. So the typical thing in NDSolve will be that we have already a coordinate system. We know what the lines are, and we are solving for functions on that coordinate system. Here, we impose some conditions on alpha and beta, like the divergence of beta is something, but we don't know beta. Beta itself is going to be solved together with the rest of the functions of the metric. I see. The coordinates will be determined by beta, but we don't know beta yet. At the very end, we know simultaneously the metric and beta and alpha. So at the end, we discover which coordinates we have and which metric we have. If we had imposed different conditions on alpha and beta, we would arrive at different functions, alpha and beta, and different functions for the rest of the metric, but the physical metric will be the same. It's just expressing different coordinates that we discovered at the end.
Right, and there are presumably, I mean, if you put the wrong conditions on alpha and beta, it may not be solvable. There may not be a metric that has, there may not be a simultaneous solution for alpha, beta, and the metric.
Exactly. We might discover a coordinate system that collapses or gets singular very soon, for example, if the conditions in alpha and beta are bad.
I mean, for instance, and this is for instance why things like maximal slicing were initially developed and why people paid so much attention to things like the 1+ log slicing conditions and the gamma driver conditions, because there was essentially a bunch of empirical work to determine which gauge conditions had nice singularity avoidance properties for things like black hole simulations.
Right. And when it fails, Jose, you were describing when you discovered that. When it fails because there isn't existence for all time. It just the whole thing, the thing implodes somehow. Is that right?
Right. There are singularities in the functions you are integrating, and of course you have to be very careful because you don't know whether that's a coordinate singularity or a physical singularity. If it's a physical singularity, it's going to appear in all choices of coordinates. But if it's a coordinate singularity, you might find some other conditions on alpha and beta, and the gauge freedom that avoids.
And it took like 50 years for people to realize the Schwarzschild singularity coordinate singularity wasn't a physical one.
That's not quite true, actually. I was looking at the history of this for this new paper. That I mean, Lemaitre worked it out about 15 years after, like in the 1930s. It's just no one paid any attention to him.
But didn't it take Kruskal coordinates and things like that before people really understood that the coordinate singularity in the Schwarzschild metric wasn't of physical
Well, okay, yes.
singularity.
So the Kruskal extension is one way of becoming convinced that it's a true singularity. But Lemaitre had actually made the argument that's, I think, a perfectly reasonable argument that, well, you know, the Kretschmann scalar diverges, right? So and we know that's a, you know,
but I was talking about the singularity at the event horizon.
Exactly.
In the original.
But that's my point, right? So Lemaitre had developed Lemaitre coordinates, which just like Eddington Finkelstein or like Gauss-Strand Panleve, got rid of the coordinate singularity at r equals 2m. But then in his paper he made this like parenthetical remark about how the one at r equals 0 has a divergence of this Riemannian curvature invariant, and therefore it's probably not removable in this way. And then, yeah, okay, no one really took it seriously until the Kruskal extension. But
I see. So he knew, but basically you're saying he knew that there wasn't a genuine coordinate singularity at r equals 2m.
Yeah, but yeah, exactly. But people knew that. Well, okay, actually, the history is a bit complicated. Like Eddington invented the Eddington-Finkelstein coordinate system, but didn't realize that it got rid of the coordinate singularity. He'd invented it for a completely different reason. And it was David Finkelstein who realized that it got rid of the coordinate singularity. So different people knew different things at different times. But
interesting. But I mean, it took until the 1950s, didn't it? Until people understood that wasn't a
probably in a mainstream sense, yeah.
Okay. Anyway, I'm just trying to understand. Okay, difficult equations. All right. Okay.
But yeah, I mean, and Stephen, it's worth commenting on that. That sort of one of the typical way that numerical GR simulations crash is that you end up with gauge conditions that sort of stretch your coordinate system infinitely in some direction. Right, that's usually the way they fail.
So maybe I'm jumping too far, but in our kind of models,
yeah,
where sort of
so in the Wolfram model case, that sort of crash mode would be one where you're only updating one region of the hypergraph, and so there are sub-hypergraphs that are just not getting updated. And so to evolve to a genuinely non-overlapping space-like hypersurface would require an infinite amount of computation, right? Because the bit that you're not evolving is never going to evolve, so to speak.
Right. So in other words, the coordinate, what you're saying is, in a kind of, these choices of coordinates are determining where the update activity is happening.
Exactly.
And in order to have a sort of
So the point is that in the discrete case, these alphas and betas have a very direct expression, right? The alpha is how many causal edges you traverse from one event to the event on the neighboring hypersurface. Beta is the hypergraph distance between the application points of the corresponding events.
Right. Lovely. Okay.
Okay. So well, with that, maybe I should show some of the numerics. I mean, I'm trying to give you some indication of how we set up the initial conditions, how we handle gauge freedom. There's a lot more to say about this.
Well, just give me some sense. I mean, if I wanted two black holes playing in the
right. Okay. So for that we could, okay. Again, you may have noticed before when we called Kerr with complete gauge freedom, it didn't evaluate because it's just like too complicated. But so I'm going to have to restrict the gauge freedom a lot to make this evaluate. But if I do this, so there are many ways to set up analytic forms of the black hole binary initial data. This is actually let's maximally constrain the gauge conditions. This is a typical one, the Brill-Lindquist initial data. So,
and that's representing a single black hole?
No, a binary black hole system. So
you have enough parameters to do that.
Well, as you see, there are defaults for everything, right? So here you can see this is the geometry of actually let's show the spatial.
So R is the distance between the centers of the black holes. A1, A2 are the sizes of the black holes or something?
No, actually, so R is the radial coordinates. M that we're assuming for simplicity that both black holes have mass m, and Z0 minus Z0 and plus Z0 are the initial positions of the two R equals 0 for the black holes. So Brill-Lindquist is one way to do it. There's also Misner metrics and other things, and effectively they correspond to different. So the way you set up analytic data for a binary black hole simulation like this is you essentially more or less set up a wormhole space-time because a wormhole space-like hypersurface, and then you treat the two mouths of the wormhole as being the two black holes that are colliding.
So wait a second. So is it the case that, I mean, if I just tell you, here are a bunch of center coordinates for a bunch of black holes, can you write down initial data that corresponds to that sort of field of black holes, or is that
there is a generalized Misner metric for essentially lattices of black holes,
but not, I mean, can I place black holes at arbitrary positions in a, like I'm placing hard spheres or something in some hard sphere gas simulation?
Not analytically. What you would need to do is do a sort of relaxation, is apply a relaxation algorithm or something to set up the initial data for that.
And the reason you can't do it analytically is, I'm just trying to understand, is that because there's not an obvious space-like hypersurface where simultaneously there are all these black holes just hanging out in the
well, I mean, there's not an obvious space-like hypersurface which admits a closed form metric.
I see. And by that you mean, so each black hole on its own has a well-defined metric, but when you bring them together, I see. It's not obvious that you can get a consistent metric that represents the combination of all those black holes. I
mean, it's actually a total fluke that we can even do this in the binary case. And as I say, it's a fluke. These come about from, I think they're often referred to as trumpet solutions or trumpet initial data in the numerical relativity literature, because you're essentially defining a kind of wormhole-like solution that looks like a trumpet. And then and actually that's the key difference between the Brill-Lindquist and the Misner metrics, is that they just have slightly different topologies. It depends on whether you treat the space-time as being one-sheeted or two-sheeted. But yeah, then the idea is you bring the kind of two mouths of the trumpet together and you collide those. And that, acts like a binary black hole system.
But this type of solution is a solution that contains singularities, but it's not a realistic solution. So if you put this into a numerical code, the first thing you will see is that it relaxes. It kind of sends to infinity a lot of gravitational radiation, and then it relaxes to a real situation with two more realistic black holes.
Right, exactly.
So people have to wait for some time until this evolves into something more realistic, that you could say these are two black holes.
And so, yeah, it's pretty standard that people will just cut. I mean, it's referred to as different things, but it's called things like ringing noise or relaxation noise. There's basically a bunch of crud that gets produced at the start of the simulation, and you just kind of ignore that, and you look at the later time behavior.
I'm trying to understand an analogy for this. I mean, it's kind of like if you had a mechanical system, and you said, "I'm going to simulate this thing under, this configuration of."
It's actually a lot like Riemann problems in fluid mechanics. Actually, mathematically, it's pretty much identical. So when you set up a shock tube problem or something with an initial discontinuity, the standard approach, if you're doing an explicit time evolution scheme, is that you drop the CFL, you drop the Courant number normally by a factor of about 5 for the first few time steps. And the reason is because you're going to introduce a bunch of numerical instabilities and dispersions around the discontinuity until it relaxes.
I see.
And you see exactly the same thing.
So it's probably the same sound waves as well. I mean.
Well, exactly. Yeah. Exactly.
Okay.
That's I think in Toro's book on numerical analysis, he calls it like initialization stabilization or whatever. It's a standard PDE problem.
Right. Okay, I get it. Okay, all right.
So this is how you'd set up a binary black hole system or something. Okay, so maybe I should say a little bit about the actual numerics side. So if we take a metric, I'm going to try and pick one that I think we can solve in a reasonable time on my not so great laptop. So if I say Schwarzschild mass 1. And let me not use the default formal coordinates. Let me use TR1A. And let's do, say, time between 0 and 1, R between 0 and 4, say, A1 between -pi. So I'm just giving it some coordinates to use, some coordinate conditions to use. And then let's do 400.
So, I mean, just talking about design here for a second. I mean, I'm kind of trying to understand when you have these TR A1, A2, is that, I mean, that depends on the metric, what those parameters are. Is that correct or is that not correct?
So those are not exactly parameters. Okay, so going to the design question, if we take Kerr, right, I can say coordinates, and it has a default choice of coordinates. but these are formal symbols because I don't want to clash with pre-existing names.
Yep.
So all I'm doing here is I'm just saying, well, instead of using that, use a different coordinate system. Use that, for instance.
I see. So it's just four coordinate, four-dimensional space-time. They're four coordinates.
Right.
It's very old style to have just four coordinates for space-time.
Well, okay, hang on. I mean, I can't remember if it's in this version of the code. It's not. I can show you a version of the code, an experimental version of the code in a different branch in a minute, which has the generalizations of these things to arbitrary complex dimensions, although they get very, very complicated because
but
effectively
it's still interdimensionality, yes or no?
No.
Really, you can define these things for arbitrary?
Yes.
Complex?
So you end up with a essentially a Hankel with modified Bessel functions and modified Hankel functions for your radial and that come from these spherical harmonics for your radial and angular coordinates. And then so the part of the complexity comes from the fact that you can no longer represent these things as as a normal tensor type thing. You have a more abstract notion of a tensor that can only be expressed through projections. And in fact, for the general discrete spacetime case, that's the best you can ever hope for, really. Okay,
but so when you say, so I understand that the generalization of to hyperspherical functions, and I'm sure the Minkowski version of that is something, maybe it's presumably Bessel rather than Gegenbauer polynomials or something.
Right.
Or Hankel, which is sort of like complex Bessel or something. Okay. But what's less obvious to me, and maybe you've solved this, is normally you've got vectors of coordinates, and this metric tensor is telling you distances between vectors of coordinates. But if you're not in interdimensional space, how are you even representing positions?
Well, you have to give it vertices, right? So I can maybe demo this
all right. Okay, so this is really going full. Hypergraph, so to speak.
That requires me running an experimental version of the code. This is the more established.
Okay, all right. But the basic point is that you say you define a position not by a collection of coordinates, which would be, what we get by defining directions, so to speak, but actually the way we think it really should work of defining position by a node in the hypergraph.
I mean, so what you're saying about the, if I say metric, so for any given metric, I can say length pure function, and it will synthesize a symbolic piece of Wolfram language code that computes distances, distances between arbitrary four vectors for the case of Kerr.
Right.
That's effectively what you're talking about. Of course, in the general discrete case, we can't do that. But what we can do is, so these are effectively projections, right? You are projecting, a given tensor in some direction. Or if we took, I said Ricci tensor that metric. Sorry.
No, but I get the point. What you're doing is you're operationalizing the notion of position. This is very lovely. And because usually you think a position is some collection of coordinates with respect to these directions in four-dimensional space.
So this is how we take an abstract tensor, or how we define an abstract tensor for a kind of arbitrary combinatorial structure, right? So it's just something that you can give an input vertex and output vertex, and you compute a projection. And so it doesn't permit a nice nice linear algebraic representation in terms of matrices or arrays or whatever. But you can effectively you can represent that tensor as just a collection of all of its projections, which is what you see there, for instance.
Lovely. Okay. Honestly, this is just. This is a very interesting merging of the. It just helps me understand the relationship of the quotes linear algebra by talking about linear algebra, you are essentially imagining that you are making, I don't know what, there's a mathematical term for it. That this, you're defining directions, which you don't get to do in a hypergraph, only as an approximation. What is that? What is that process called of defining directions? And it's some kind of.
It's effectively defining a local coordinate basis. Right.
Yes. In fact, the notion of coordinates as such is a notion that is beyond the hypergraph story.
Well, so the point is that it requires having a notion. I mean, that's what the notion of connection does, right? And so the point is that connections work connections are much more general for hypergraphs than they are for Riemannian manifolds. That's the kind of the big picture story.
Okay, explain that statement. I mean, so a connection usually is giving you the mapping of coordinates from one place to another, but you're saying here, how should I think about the generalization of that?
So a connection here tells you effectively, it is essentially a rule for how you lift. For how you lift perturbations in where you apply a hypergraph rule to hypergraph distances in the hypersurface.
Well, right. I mean, the little piece of coordinate system. Yeah, I mean, you could look at a local region of hypergraph around some node, and you try to match that up with a local region of hypergraph around some other node. And you're asking what transformation should you make? And I don't even know how to parameterize that transformation.
Well, this is a topic for another discussion, but this actually relates to some stuff that we've been working on recently in relation to these algebraic quantum field models.
Okay. Which is
Okay, so there's an evolution. Okay, this is a static metric, so it's not a very exciting evolution, but there's the evolution parameterized in terms of hypergraphs. So what's happening here is, in the general case, what we're doing is we're saying, okay, we take the initial data, we produce a hypergraph by a Poisson process that agrees with the continuum metric up to some discretization scale. That's what the one is doing here. And then we just evolve the thing in time as a Cauchy problem using, in this case, the ADM equations, although there's experimental support for BSSN and CCC4. And I hope to also support other kinds of initial value formulations.
Okay, so but there is an underlying hypergraph rewrite rule, or you're evolving.
So there is an underlying hypergraph. There's an underlying hypergraph rewrite rule, which is what's doing the refinement and coarsening. Mm-hmm. There are two, right? There's a refinement rule, there's a coarsening rule. And then we're applying that rule in places where it should be applied according to the rules of AMR. And so effectively what we're doing is we're defining a Wolfram model system whose event selection function is determined by a PDE system.
Okay, but the PDE, so are you labeling the nodes in the hypergraph by some continuous parameter or what?
Yeah. So but then, as I say, the interesting thing becomes that then we can reconstruct those continuous parameters from the hypergraph structure. And this is what there's some research work going on at the moment about exactly this, about how much information you lose if you actually just kind of throw away the PDE system and you just retain the hypergraph topology. And the answer is you lose a lot, but not as much as you might think. And with a sufficient
and in the end, in the world, I mean, we've got a lot of orders of magnitude between the actual discrete microscopic structure of space and what we actually observe. And to parameterize those many orders of magnitude, it is not an unreasonable thing to think about just labeling the nodes of the hypergraph by some continuous parameter.
Right. I mean, yeah. So in effect, you can think of the non thrown away version as just being a sort of coarse-grained approximation of a sort of pure underlying hypergraph rewrite.
Right, but the thing that you're doing here, in a sense, is, I mean, if one was doing finite differences, finite elements, whatever, well, actually, I don't even know the answer to this. This is a Rob who's been quite silent, or Jose probably knows this, or anybody here other than me knows this. I mean, in a standard finite element evolution process for a, let's say a random hyperbolic PDE, does one routinely change the mesh, or is the mesh something which is fixed given the geometry of the problem? I mean, in other words, is this thing, because this is something which by its own dynamics is changing its analog of the mesh. I mean, is that something that in the world of numerical analysis, is that something people routinely do, or is that something that is kind of hard to do consistently, which is where these models should come in, is forcing.
I mean, I can take a crack at the answer, which is that, so there's adaptive mesh refinement does that in a very limited way, or in a very restricted sort of way, right? So the algorithm that's being used here is a sort of is a generalization of this thing called the Berger-Oliger method for adaptive mesh refinement in finite volume PDE systems. So the idea there, in the standard case, you would have like a Cartesian mesh. And then you'd say, okay, well, if you have some indicator function in each cell, and then you say, if the indicator function exceeds some value, then we hierarchically refine that cell. And if it goes below a certain value, then we coarsen that cell. And then you have some ways of sort of projecting fluxes and things from coarse cells to fine cells. And there's a bunch of complexity about how you modify the stable time steps in the finer regions and stuff. But that's the basic setup.
Okay, but so it's kind of like a tree-like hierarchical. I mean, in the end, you're going to get something that has, additional layers of tree branching in certain places in the mesh.
Right, and in fact, there's a method called adaptive refinement trees that does represents it exactly in that way. And then in numerical relativity, people developed a bunch of methods for doing AMR with more general kind of curvilinear coordinate grids. But
what is AMR? Sorry, adaptive mesh refinement.
Adaptive mesh refinement.
Yep.
But so this method is a little bit different, at least from those. And again, this is maybe something where Rob will know, because I don't know that much about the finite element world. I know more about the finite volume world. But at least in the finite, so this is doing something that's a bit different because it's keeping the topology of the hypergraph essentially completely unstructured, right? So normally you would say, I hierarchically refine the cell, but I keep, it's like a self-similar coordinate grid, right? Like I'm still preserving the kind of Cartesian coordinate topology. It's just like at a smaller scale. Or in other words, the changes to the mesh topology that I'm making by doing the adaptive refinement are very, very restricted. Whereas for this algorithm, they're completely as unrestricted as they can be, because our coarsening and refining and coarsening procedure is given by hyperedge subdivision and hyperedge smoothing. So you literally just take an edge between two vertices, and then to refine, you just plonk another vertex in between. And to coarsen, you just take a path of three vertices and you extract the vertex in the middle. And I don't know, I suspect that is sort of theoretically the most unstructured form of mesh graph refinement that you can do.
All right. Anyway, so I think we understand roughly the framing of what's going on. So now, all right. So you've got, well, keep going. You had an arc of presentation here.
Well, I don't know. I'm trying to give a kind of a high level overview of what's going on. I don't know what I mean.
Okay. So what you're first of all defining is how do you set up the initial conditions, and in terms of software design, it's like, imagine, if I were to want to put black holes on the corners of a pentagon or something, on the corners of a dodecahedron,
right?
What would can you do that?
Not with the framework as it's currently developed, but I do. As a kind of general design thing, I do want it to be as modular as possible. So for instance, right now, so we've been dealing only with sort of vacuum spacetimes so far. So if I say solve vacuum Einstein equations, we've been taking things like the Schwarzschild metric. And it's assumed a non-zero cosmological constant, so it's saying that it's not a true solution. But okay, there we go. So that's it can confirm that is in fact a solution, and it's an exact solution. It's not some, hasn't had to make some numerical approximation or whatever.
Well, how can you visualize that? So that solution, I'm confused. Isn't the metric the solution, so to speak? What does it mean to solve the Einstein equations beyond?
Well, no, the metric is some arbitrary. So the point is, you can put some completely random matrix into metric tensor, right?
Yeah. Okay.
So only some of those will be true metrics that are that solve the Einstein equations.
Yes.
And so that's what solve vacuum Einstein equations is checking. It's checking. So it's computing Ricci tensor, Ricci scalar, Einstein tensor, and then checking that that's equal to 0.
Okay, but wait a minute. If it's saying solve, normally solve would be given a set of conditions,
right?
Generate me a solution. But this doesn't seem to be doing that.
So if I say, FLRW or something, right? That's not a vacuum solution. So if I say solution 2 equals solve vacuum Einstein equations. Okay, but I'm going to keep the cosmological constant in just for fun. So it's saying not an exact solution, and it's saying 4 field equations. So here are the equations that would have to, it's the minimal system of equations that would have to hold in order for this to be a true solution to the vacuum Einstein equation.
Okay. So this is the analog not of solve, but of reduce, I think.
Maybe it should be reduce, yeah.
Right, because I mean, what this is doing is it's giving you, or is it even maybe something even slightly different from that? It's giving you the subsidiary equations that would need to be satisfied in order to have, you have something with more parameters, and it is telling you these are subsidiary conditions that have to be satisfied for these things, for this to work. But now if I were to give it a metric tensor that is an explicit metric tensor, just some random matrix,
yeah,
it's just going to say, what's it going to do? It's going to say, forget it. What's it going to do? What does solve Einstein equations vacuum?
Well, okay, if it's truly a numerical matrix, I mean, this is where we get into the problem with physicists calling things tensors that aren't really tensors, right? So the metric, normally when we say metric tensor, we don't actually mean metric tensor. We mean metric tensor field, right? The Schwarzschild metric is a metric tensor field over a geometry, so it has coordinate dependence. If you truly meant just a metric tensor, as in like a numerical matrix, then there isn't even a sensible way of defining Einstein equations for that, right? It's just a sort of.
Well, I mean, the derivatives are all zero. It doesn't depend on.
Exactly. So I mean, if I say, I don't know, the best way to do this, random real, does that work? Yeah.
Yeah.
Or let's do 4, 4 or something. Oh, right. Yeah. Okay. It's going to complain because it's not.
It's not symmetric. Make it symmetric.
Yeah.
Okay. How do we make? Hey, somebody here, Rob, knows how to make a symmetric matrix. Well, you can do it just by adding it.
Symmetrize.
Oh, is it symmetrize?
Oh, symmetrize?
Yep.
Nice.
It's going to give you a symmetrized array. If you don't want that,
do
normal.
Okay.
Do normal then.
Yeah.
Normal is symmetrize with that.
Yep.
Okay, so if I do that and then solve vacuum Einstein equations, okay, well, it's obviously it's going to say with 0 cosmological constant. It's going to say
all 0. So if you just say, so look inside that object. What is it? What's inside that object? That vacuum.
I mean, so yeah, I mean, inside that is not very much, right? If I say field equations, whatever, it's going to say there's nothing. But what I could do is I could say Ricci tensor of that.
And it's just going to be 0.
And that'll be identically 0. Ricci flat Q will return true.
Okay, great. Okay, so now let's just try, because let's just try making a uniform gravitational field, which is, well, even a metric. What the heck is that in terms of metric? I'm just thinking if the metric was just equal to R, for example, given
every projection.
Yeah, I'm thinking. Well, I don't know what is a uniform. What is the metric for? It's probably something much more complicated. But I'm just trying to think of the most naive. It's not really the metric; it's the gravitational field, which is more complicated to compute. But just do something where the thing, yes, it's constant like that. Now say solve vacuum Einstein equations. What's it going to do? Splatteroo. Okay.
Singular matrix.
Well, wait a second. Is that? Okay.
Sorry, just quickly before we do that, I did want to show just as a so if I give it a stress energy distribution, right? So if I say tensor, let's do perfect fluid or something. So that's going to look like this, but let's say stress energy not for Minkowski, which is the default, but for Schwarzschild. No, let's do FLRW. Sorry. So then what I can do is I can say solve Einstein equations. That and there we go. Okay. And so that will derive the general form of the Friedmann equations for arbitrary cosmological constant and an arbitrary.
Okay, so if I were to say, I have no idea what it does, but I mean a perfect fluid like in the Kerr metric, what the heck would that look like?
It will be ugly. There we go. That's what the stress energy tensor looks like.
For a perfect fluid.
For a perfect fluid in the Kerr geometry.
Which a perfect fluid meaning it's isotropic pressure and all that kind of stuff.
Right, exactly. So the perfect fluid is the one that's just equal, where it's just rho plus p u mu u nu plus p times g mu nu.
Okay. And so now what happens if you try and solve the Einstein equations in that?
Let's have a look. It may not be able to do it, or may not be able to do it in a reasonable time. We'll see.
But what would it mean? I mean, so it is.
So what it's doing, I can break down its computation, right? If I so it's taking the Kerr geometry, it's saying Ricci tensor, metric tensor Kerr. Okay, so obviously so we know that the Kerr is a vacuum solution. So this will return a non-zero thing. It'll return some big complicated matrix, but if I say reduced matrix representation, which will kind of simplify by all known algebraic equivalences, it will reduce to a zero matrix. So all it's doing is it's saying it's setting up the mu nu minus, and of course we could say Ricci scalar and all that kind of stuff.
But I mean, but these things certainly at the origin, it is not the case that the Ricci tensor is zero, correct? I mean,
well, it's not defined. The metric isn't defined at the origin. So
okay.
It's I mean, this is why, in a sense, why one tends to say that black holes are like gravitational solitons, right? Because they are just like, they're vacuum solutions, except for like a kind of delta point, delta function point.
Yeah. And I mean, I don't know the taxonomy, the zoo of solutions, but are there solutions? Okay, naive question. Are there solutions known? I mean, there are solutions where there is a point carved out of the manifold. Are there solutions known where there's like a line carved out of the manifold?
Well, in Kerr, it's a path, right? It's a ring.
Right.
And there was a recent, I mean, okay, basically, my understanding is there's comparatively little known about what the topology of possible, what topologies of possible space-time singularities can exist. Like a question I've always been curious about is, can you have ones with kind of arbitrary ambient isotopy groups? Can you have a singularity that's that's isotopic to a trefoil knot or something? And I have never been able to find the answer to that question. I don't know if Jose knows anything about singularity structure.
No, I cannot.
No, that's interesting though. Okay, and I mean that that whole thing, in the case of hypergraph rewriting, that what does that mean? I mean, so when there's a point singularity, it means there is a place in the hypergraph where no more rules apply. And
okay. So yeah, right. So okay, this is actually the topic of the paper I'm working on. This is the thing in the background, right? This is me investigating. The idea behind this is to look at, are the singularity theorems true in discrete spacetimes, and what do you need to modify about them? Like, are there any differences, right? So here's like an example of a gravitational collapse of an initially spherically symmetric mass distribution to a Schwarzschild, to something that limits to a Schwarzschild geometry. Here's the corresponding down here. Here's the corresponding gravitational collapse to a Kerr geometry, an extremal Kerr geometry. That's the initial scalar field configuration, and this is what it collapses down to. And so
should I consider it significant? There's a big gap in that hypergraph.
Well, that's effectively the interior and exterior event horizons separating off from each other.
Really?
Yeah. And so actually in the limit case, it splits off. As the point is, as J over M goes to 1, the hypergraph becomes disconnected in that limit.
Well, I know that, but I mean, so if you did that for a Schwarzschild, in the Schwarzschild case, there is no similar disconnection. Is that
no? This disconnection occurs entirely because of the non-trivial event horizon structure of Kerr geometry as it approaches extremality.
And what happens is there any way of getting other? I don't remember. Does like Reisen and Nordstrom have different? Is that just like Kerr, or does it have extra stuff in it?
It's pretty much like, I mean, like we support it. I mean, but you wouldn't want Reisen and Nordstrom. You'd want Kerr-Newman, right? Which is, Reisen and Nordstrom is non-rotating charged. Kerr-Newman is rotating charged. Okay. So this is what Kerr-Newman would look like. But effectively, it's like the same geometry. But the charge here, Q, just has the effect of changing the effective mass.
Okay, that's not interesting.
The only difference it makes.
But okay. All right. I mean,
sorry. What I was going to comment about that though was the the way that the way that singularity is defined in the context of the singularity theorems is in terms of geodesic incompleteness, right? So you essentially say you take a geodesic congruence, and then you ask, can I extend these geodesics arbitrarily far as analytic functions of the affine parameter or the time parameter? And if the answer is no, then we can say, well, that's probably because they've hit some space-time obstruction. And then the essence of the singularity theorems is showing that from the Ray-Chowdhury equation that describes how the geometries of those geodesic congruences evolve, that as long as you have a trapped surface and you have reasonable energy conditions, that you always get geodesic incompleteness. So that the nice thing is that admits a very natural formulation in terms of hypergraphs and causal graphs, because you can see it right over here somewhere.
I'm about to ask about the no-hair theorem and how you see that in a hypergraph. That is
okay. So this is an example of a singularity signature in the causal graph, right? So there comes a point where this causal geodesic just cannot be extended, right? So the causal graph just ends at that point. That path has finite length, and however much you apply the hypergraph rules, that path is never going to extend. That's the analog of geodesic incompleteness. And so the analog of the question we were just asking would be, can you have a congruence of geodesics in the causal graph that cannot be extended by applying hypergraph rewriting, where the endpoints of that congruence form a topologically non-trivial structure in the hypergraph?
Yes.
And
the answer is?
I don't know.
Okay. Might be known in a few weeks, but isn't known yet.
We don't know in the continuum space-time case.
No, I understand that. Okay, that's been 100 years, but that we're expecting faster turnaround here.
Well, at least we can test it reasonably systematically, I guess.
Right, but okay. So just is there an intuition about the no-hair theorems of why, from an arbitrary configuration of initial hypergraph, that there is some sense in which is that obvious from what you? I mean, is that?
It's obvious as long as you don't have long-range hypergraph connections. I mean, all of that's saying is that once you've collapsed beyond this region here, if you're on the outside of this hypergraph, then the only features of what's going on inside this region that you can extract are very, very coarse. I mean, that's really what the no-hair theorems are saying.
Well, right, but it's saying that the connection between the inside and the outside is through hypergraph. You're saying if there were things that reached kind of wormhole-like things that reached right into the center, then you could be detecting features of the center from far away. I mean, insofar as most of the distance on the hypergraph, it's this thing with threads that I wondered about ages ago.
Right. I think I mentioned this in an email, but my new conjecture is that your quantum mechanics idea from NKS is much more plausible as a dark matter candidate than as a quantum mechanics candidate, in my opinion.
Yes. Well, let's think about that for a second. So, so you're saying
the point with the no-hair theorems is, okay, so as a general feature of these hypergraph models, one of the things it means, okay, what's it mean to say that it has a continuum limit? Well, one of the conditions that it has to satisfy in order to have a continuum limit is that it doesn't have arbitrarily long-range connections between different points in space, right?
Yes, or at least not many of them.
Well, yeah. They have to form a vanishingly small subset or something. Yep. And so that effectively means that the amount of information that you can glean about a distant region of the hypergraph is necessarily limited if you're in some other region of the hypergraph.
Yep.
And the no-hair theorems are just the special case of that, where it says, well, if you're on the other side of the event horizon, then you have limited information. There's limited information you can glean about what's on the other side, and so the no-hair theorem is like the theorems are sort of the degenerate case where it says, well, actually the only things you can deduce are mass, angular momentum, and charge. So the long-range connection thing would be saying, well, maybe there are cases where that isn't true, where some degrees of freedom somehow leak out. And so you can have kind of black holes that exert gravitational influence over a much larger region of space than they should, according to the continuum theory. And if that happens for, say, supermassive black holes, that could potentially extend galactic halos and stuff.
That's amusing. I mean, but what would it actually look like? I mean, is it a correction to the 1 over r potential, so to speak, 1 over r, the the normal. What it's going to do is it's going to change the geodesic. It's going to change the area of the geodesic ball, so to speak, by having. Go ahead.
It would effectively say that the weak field limit in GR is not valid in the places where we think it's valid, right? So it's standard to, and it's a common way that you derive things in GR. Is you say you want consistency with you want the Einstein potential to be consistent with the Newtonian potential in some weak field limit. So you want the 1/r², phi thing. But if there are long range hypergraph connections, then that's not going to be, then it's not going to be the case that, even arbitrarily far away from a Schwarzschild black hole or something, it's not going to be the case that the weak field limit necessarily apply. You don't get, or asymptotic flatness doesn't mean what you thought it meant, so to speak.
Well, or put another way, I mean, you're trying to fit. You've got this hypergraph, and you're trying to model like a manifold as, Euclidean space is the microscopic model of what's happening in a manifold. And in a sense, what you're trying to do is you're trying to fit, I'm trying to understand this, you're trying to fit some continuum picture on top of something which has a bunch of threads in it, a bunch of long-range threads. And the question is, what does the fitted continuum picture, what does that look like when there are these long-range threads? I mean, in other words, if you
presumably it's the standard way to do it would be to have some, would be to change the homotopy group, right? It's just to say, model those long range threads as like little, wormhole like things that induce holes. But the point is,
what happens if there are a large number of microscopic wormholes that reach from the center of our galaxy to the outer reaches of our galaxy? What does that do?
I don't know.
Let's think about it for a second. I mean, and those wormholes, it's not like, you'd normally think about those as being in space, but they're not in space. It's not like, oh, you're traveling around in a spacecraft and suddenly you reach one of these, you reach the edge of the side of a wormhole. There is no side of the wormhole. The wormhole is reaching from place A to place B, not going through what you attribute, as your spacecraft goes along, it can never go into that wormhole, so to speak, if that makes any sense. In other words, the wormhole, this thread is going, let's say, from the center of the central black hole of the galaxy out to some random outer, it's terminating somewhere. When I say it's terminating somewhere, what I mean is that there is a background sort of manifold-like modeled by Euclidean space at a small scale, or Minkowski space or whatever, at a small scale thing. But and when you're tooling around in a spacecraft, that's all you'll ever see. And the question is, what would happen is, if you look at the, so to say there are additional threads is to say that, let's think about this. Is this obvious? There's some obvious way to think about this in terms of just, normally the volume of that geodesic ball is r to the d, but somehow the number of let's think. Well, I can't quite figure this out in real time, but maybe
since you bring that up, sorry, I don't have an answer to your question, but since you bring it up, and since I know it's one of your favorite features of Riemannian geometry, I should just say that we can do things like is it? I think it's volume.
It's about the only one I know.
Volume expansion. I can't remember the property names now. Scalar volume expansion. So it will. This is the expansion of the volume of a geodesic ball relative to the volume of the corresponding ball of the corresponding radius epsilon in Minkowski space.
Oh, that's lovely.
The unsimplified form, if I do the simplified, okay, well, this is a vacuum solution, so it's simplified to something trivial, but it can also do the directed case, right? So you can say things like volume form expansion, and that will give you, so this is now the volume of a geodesic cone projected in a given direction relative to the volume of the corresponding cone in Minkowski space. Things like that.
Well, okay, so there's a lot of very interesting stuff here. So let's talk about okay, we had wanted to make sure we covered sort of software design aspects of this. I mean,
right. I mean, so
nice
I have three primary concerns, right? Which were the reason I wanted to call this meeting.
Mhm.
One is I want to make sure that whatever you and the institute and things have planned for numerical GR, that it's, you know, that we're not duplicating effort, and that this is sort of the kind of thing that you want.
I think you've gotten a lot further than everybody else has got. So
That may be true, but also, I mean, is this?
I don't actually know what the plans are there, so I'm it's not an event horizon. It's just a lack of. It's just my let's put it this way. Yes, it is an effective one because I've been accelerating in other directions, which have caused me to not be able to get signals quickly enough from that. So yes, so I don't know. Good question, and I don't.
Okay. And then, but so the other two things that slightly worried me are, okay, so obviously in doing this, I've had to implement a bunch of symbolic tensor functionality, both sort of tensor algebra stuff for doing, you know, raising, lowering indices, doing contractions and so on, but also a bunch of tensor calculus stuff. So if, you know, if I take this, you know, I can say whatever, covariant derivatives or something, and it will compute an association of all covariant derivatives of the Ricci tensor. And so, you know, so it's nowhere near as general as something like exact, where you can sort of build up arbitrary tensor equations and things. But it's the goal, at least my goal, was to have all the sort of tensor algebra, tensor calculus functionality that you would want to have in a basic kind of general relativity package, all
right
in one
which
place.
I don't think we've, you know, I mean, Jose should comment on this, but I feel like the convenient things to do for general relativity are the things that we might do for sort of completely general tensors are not particularly convenient. You know, if that's what we're doing, it won't be particularly convenient for general relativity. I don't know. Jose, do you want to comment on this?
So I think there are some things here which would be quite useful as individual functions, like computing the Ricci tensor from a metric. It's a standard computation that people would appreciate. And I've seen that exists already as a WFR function. So that type of thing, it takes some time to set up in exact, because in exact you have to set up first a manifold and a coordinate system. So it's multiple lines of code.
Mm-hmm.
While here I see you can do it quite quickly, which is nice. But then yes, this type of approach can do what can do, but you cannot build up general things.
Because what? Because why?
Because you may want to have arbitrary objects that your problem has, like suddenly you want to have a new vector obeying some properties with respect to some other derivatives that you have introduced, right? So the way this works in exact is by setting up a bunch of objects that at the end you are going to use all together. And people will spend some time building up the environment because they know they are going to be working quite a lot with that environment for whole paper, many equations, that sort of thing.
Right.
So this is kind of the dual approach, which the users of exact have complained about sometimes. So it takes some time. It takes much time to get to some easy.
So another question is the bridge between this and exact,
right?
And whether there's a, you know, whether you could essentially generate exact stuff from this easier to get started with technology.
I think that's probably a very sensible thing to do, because yeah, like as Jose said, you know, the key limitation with this is obviously if you wanted to build up some arbitrary, some new tensor, right? That's some combination of, you know, contractions of Riemann tensors and Weil tensors or whatever. Like, there's no way to do that. And to do that in generality, you would need a framework that is at least as powerful as exact. And, you know, I have no plans to implement. You know, that's already been done. I have no plans to re-implement that. So exact feels like exact fills a different niche. If you just want to do kind of fairly standard general relativity calculations, I'm trying to make that as easy as possible to do with this. But as soon as you want anything more advanced, you probably will have to go to exact or something equivalent.
Okay, but let's talk about the workflow here, because I mean, you know, one of the things, I mean, I have a parochial interest here in just being able to do enough general relativity with something that has, you know, an underlying, you know, hypergraph structure that you know, that we can study the, you know, the phenomenology of those things.
Is this workflow straightforward? I mean, is this kind of what you had in mind? So this is an important.
I think so, but I just haven't thought through what. I mean,
and I mean,
let's take the example of the galaxy with its central black hole. Okay.
Okay.
Let's imagine that we want to actually solve. We want to know, does this make dark matter?
Right.
Okay. Let's talk about what would be involved in doing that. So we'd have a central black hole, and we'd ask the question. What we might be asking is, given some distribution of mass or something, of things falling into the black hole, is it the case that the hypergraph we get has little tentacles coming out of the black hole? And what effect would they have? We presumably want to watch a geodesic move around the thing and ask questions about, you know, what it does.
Let's show how you would do that, right? So if I say something like this, so there are various, I mean, just evolving the metric is one class of numerical computation you can do, but there are various kinds of numerical computation that you can do with, this is it currently functions. So hang on, let me think about this for a second. I want initial coordinates, something like that. So it's outside the event horizon. Let's do, I think the orbital velocity for a mass, for a unit mass black hole is 1/8. So let's say L is our affine parameter. Let's do that as our coordinatization. This may or may not work. Let's have a look. So the, I mean, and the way that this works is due to a very nice correspondence that we've known about for some time between essentially solving geodesic equations in Riemannian geometry and producing, you know, and finding shortest paths in graphs, right, with some weighting. So this is a Schwarzschild geometry with a geodesic. This should be a circular orbit.
Oh, hold on, wait. Okay, so the background graph here is what? Before you put the geodesic on it.
It's the Schwarzschild metric.
Okay, just redrew itself in a weird way. Okay.
Yeah, I mean, I can coordinatize it if you want.
No. I'm happy with that. So then what you're saying is, if I look at those geodesics, then the question is, I mean, because what you want is an evolving black hole, which isn't, I mean, what if you just take the Schwarzschild metric and you sprinkle the Schwarzschild metric, you've already cooked the answer, so to speak.
Right. So this is why, so in general, you would want to, so this metric tensor would be something that's produced by ADM decomposition, right? So you would, so the workflow is, you set up the initial hypersurface geometry, you ADM decompose it, you impose whatever gauge conditions you want, you get out a symbolic metric tensor, you then discretize it using this function, and you give it some parameters, and you evolve the thing in time.
Okay, but so a naive thing to do would be start off with sort of the galaxy as it was when it was young, so to speak. I have no idea. Are there? This is a. I sort of have a. I sort of booked a time to talk to a old astrophysics cosmology friend of mine about this, but we haven't gotten around to it yet. You should join that. Okay, are there age effects in dark matter observed in galaxies? Do you know? In other words, if you look at a young galaxy, like I know there are galaxies now people have found, I mean, recently, a few weeks ago, is announced like galaxies from 130 million years after the Big Bang. Does one know if there are different rotation curves for galaxies that are really old compared to newer galaxies?
I have no idea.
Jose, do you happen to know?
No, I don't know either.
My guess would be no.
Yeah, it's what I haven't ever heard of that. I mean,
exactly. It's one of the things where if there were a discrepancy, I would have thought I'd know about it. But
right, unless it's hard to measure the rotation curves. But okay, but so then, I mean, the question would be, if you have a thing that is going to, you know, like, okay, here's another naive question, which I don't know the answer to. If you look at a galaxy as a function of age, like our galaxy, I don't know what it's, you know, whatever it is, it's, how old is our galaxy anyway? I don't even know that. It's terrible. I don't know that. I think it has a 200 million year rotation time. but I don't know how old it is.
I only know that from the Monty Python song.
Oh,
Our own galaxy, you mean?
yeah. How old is our galaxy?
I mean, it has gone many rounds, so I
No,
don't
no,
know.
I know that, but I
10
mean,
10
but
billion,
is it? You think it's 10 billion years old?
something like that.
I don't know. I have no idea. I mean, we're not a first generation star, but in yeah, I don't know. I see a thing saying the web says 13.6 billion, but I don't think that's necessarily at all correct. I mean, that would be
That would make it very young.
no 13. That would mean it was 1 billion years.
Well, yeah, I mean, sorry, as in it was produced when the universe was very, sorry,
Yeah,
yes.
I don't think it's realistic at all. I think that's only at a very high redshift that you get to something like that. Anyway, but my question would be, okay, so the question I was going to ask is, can you compute?
Oh no, okay. Google does, and okay, hang on, wait, let me check the source of this. There are a bunch of people saying that some parts of it were formed about 800 million years after recombination, which would, so 13.6 billion is not too far.
All right. Okay. Well, then the question is, how has the size of the central black hole changed over time? Presumably there are unlucky stars that fall into the central black hole, but I have no idea what causes. I mean, there's some viscosity, presumably, that's causing them to lose angular momentum. Yeah, anyway, but the question would be, okay, there's clearly a bunch of astrophysics that I need to learn here. But I'm just trying to understand in terms of the workflow of this system.
So I mean, I think what you, I mean, so here you can, this is the time. So here we're evolving both the metric and the this geodesic, actually not as functions of time, but as functions of the affine parameter, although you could evolve them as functions of time. So you can do kind of co-evolution, and you could do this with, if you took a stress energy, I won't do it here because it would take too long. But if I take a stress energy distribution like this, then obviously it has certain continuity equations that it has to satisfy, which effectively just say that the covariant divergence goes to 0. And then, so if you close the system with constitutive relations, i.e. with an equation of state, then you can co-evolve a metric and a stress energy distribution in time together. So you could use that to simulate things like, fluid accretion onto black holes or whatever it was that we want to do. So the basic workflow would be, set up the metric, or possibly the initial data for the metric, set up the matter fields distribution like perfect fluid or whatever it is, then co-evolve the metric and the matter distribution, or the metric and the geodesic or whatever, forwards in time, and see what happens.
Okay, so we're about to run out of time. Unfortunately, we'll have to continue another time. But big class of questions, right? So this is supposed to reproduce the Einstein equations, and there are sort of numerical analysis. I mean, because basically the big picture would be, number one, does it reproduce the Einstein equations when it should? And number two, if you kind of overclock it and start having it show its hypergraphism, what happens?
Right. I mean, so there's an interesting quasi-philosophical point, which is that in conventional numerical GR, there are a bunch of situations where you'll get some crazy answer and you'll say, oh, well, this is clearly just like a grid effect.
Yeah.
The point is that actually with a lot of the stuff that happens in the physics project, it's exactly the grid effects that we want to see.
Exactly. Yes. We want to overclock the thing and watch the thing fall apart.
Right. Like for instance, okay, so with Cartesian or even with curvilinear grids, with finite volume schemes, if you have like a shock wave, say a strongly relativistic shock wave, then you get a bunch of dispersions that occur normal to the cell boundaries. So you get sort of a lot of kind of numerical dispersive noise that happens when as the shock front passes through, and a lot of effort is put into trying to tame those dispersions and introduce synthetic diffusion terms and things to get rid of them. But obviously, an interesting question is what happens if you don't get rid of them and you do the thing in a more general hypergraph topology? Would you start to see deviation if you've got a relativistic shock front moving through a hypergraph? Do the gravitational wave signatures look different or noticeably different?
I bet you'll have shot noise of some kind in the gravitational waves.
Right.
That would be very cool. And now the question is, well, what? So, okay, so this thing, relativistic shock front going through, producing what, I would qualitatively think of as sound waves. And okay, so here's the question, I suppose, for the, okay, we already have a model of this, which is molecules, right? So when a shock front comes through, a hypersonic shock comes through, and there are effects that are associated with, they're almost chemical effects associated with molecules. When you get whatever it is, the Knudsen number or whatever, well, it isn't quite the Knudsen number, it's a different, when it's a strong enough shock that, okay, the question that one should ask perhaps is, how does the presence of molecules, how does the fact that the shock goes down to the level of molecules affect the sound that is generated from a hypersonic shock?
Right.
That would be the physical, that would be the everyday, quotes, everyday analog. So in other words, if you are hearing the space shuttle or whatever, or some modern analog of that, which re-enters the atmosphere at what, Mach 25 or something, its shocks are very, they're small compared to the mean free path. I'm sure there are molecular effects. What does that mean for the distant, the non-near field sound waves that are being generated from that? One should just, one could look that up. I don't know what the answer is, but so that's what one's asking is, what are the non-near field gravitational wave effects from a relativistic shock going through space-time? And what would make it, what kind of a thing would happen there? Well, the most obvious signature will be something in the frequency spectrum. And in particular, something where, the cool thing to happen would be that there's something that you see in just like in the, when you get to the edge of a boron zone in condensed matter physics or something, where you see the lattice effect, that you see some bizarre redshifted version of that causes some cliff in the frequency spectrum of the gravitational radiation that's coming out. Right, that's a good phenomenological physics exercise, which I am way too rusty at to be able to do in real time. But that's a super interesting. Being able to validate this. So that's the question. Validating this against the Einstein equations, so that one knows that it's going to give. If it gives as decent results as your average Einstein equation code, for the cases where, what do we know? We know that black hole mergers work roughly as the Einstein equations say they should work. And
right, and this has been, we've done, well, I've done some convergence analysis against some standard numerical relativity test cases. So there are things like these have weird names, like the Gaudi wave test and the apples for apples test, and right up the way to head-on collisions between black holes and things. And we get quadratic convergence to, or at least quadratic convergence to the standard solutions. So
but that's not trivial. Aren't the standard solutions? Isn't this usually a supercomputer adventure to do any of these numerical GR solutions, or is that, or is it? Yeah.
Or at least for reasonable mesh sizes. Yeah.
But so is this competitive with that? Can you, if you make, a big enough hypergraph, how big do you, to make something that is competitive in terms of precision with typical kind of supercomputer, finite volume, whatever it is, approximations, what does it take? How big a hypergraph do you have to have?
So you can get away with sort of ostensibly lower resolutions precisely because there's more information encoded in the hypergraph topology. So for, as a very basic test case, I was looking at these relativistic shock, these Riemann problems for relativistic shock waves. And it seemed like you could get, so to get something that was comparable with having 1,000 cells of a standard Cartesian grid, you could get away with having on the region of 200 to 300 vertices in a corresponding hypergraph representation.
Wow. Well, we should do it for elasticity theory as well, because that's if it would work, if it did the same kind of thing for elasticity theory, that would be a hugely useful thing, I think, in the PDE world. But to give me a sense, I mean, in modern, when people do official black hole merger calculations, how big is their mesh and so on?
Okay, that's precisely because of AMR. That's a complicated question to answer. So, I mean, for instance, this one of the test cases I was comparing against, they started with a base grid resolution of, I think, 800 by 800, okay. but up to 4 levels of refinement depth.
So 800 to the 4th power, or what? For the
they were showing 2-dimensional projections of the surfaces, so it was 800 by 800, but 800 to the power 4 for the overall.
Okay, so that's
800 to the power 3, because you're evolving the 3-dimensional.
So that's not a huge amount of memory. I mean, we're not talking about. I mean, is this in the usual case? Is this a GPU adventure or is it that the mesh refinement causes you to not be able to parallelize things in that way?
It certainly can be parallelized, but that's an open area of research, is how you parallelize AMR algorithms, just in general numerical analysis.
Right, but I mean, so the thing I'm trying to understand is, if it will be good, it seems to me, to be able to do a really high accuracy, black hole merger calculation with this technology. And I'm just wondering, as a practical matter, how does one do that? I mean, is it like get a big computer and just run what you already have, or are there more steps that have to be done?
I think that's pretty much it. I mean, the only thing that's complicated. Okay, so the point is that the bottleneck, or at least the thing which you can readily parallelize, is the computation of the fluxes, right? So across each edge, you effectively have to compute an intervertex flux, and those can be fully parallelized, right? They don't have any interdependencies on each other.
Yep.
And so that would, if you could probably wouldn't require that much modification to the code, but if you could shard that onto different parallel instances, then you could quite easily run that on a cluster with probably reasonable speed up.
Right. Although you have to be able to communicate back the results of the fluxes. It's not obvious that I mean, it's a complicated question whether the communication.
Well, I mean, actually, the reason for doing the intercell flux or the intervertex fluxes is precisely to make it not a complicated question, because the point is that's is it embarrassingly parallel? Is that the phrase?
Yeah.
It's one of these things where you literally just, all you have to do is send to each thread a collection. Well, for a 4th order scheme, you'd have to send 8 vertices. The information in 8 vertices. It goes away, does some numerical PDE solving, sends back a number. Once all the threads have computed their number, you send them back to the main instance. Then you run your time evolution step and you do the thing again. There's no complicated coordination or anything required.
Yeah, except you have to sort of synchronize between each step, which is not, like if you're doing a cellular automaton, for example, you could be just the stuff that's happening over here really can happen independently of the stuff that's happening over there. You don't have to synchronize by time step.
The problem is if precisely the thing you want to investigate are long-range connections in the hypergraph, you can't make that assumption anymore.
I know that, but I suspect that most of we haven't really worked that hard on parallelizing this hypergraph stuff, and I bet it can be parallelized, perhaps more so than the adaptive mesh refinement can be parallelized. But I guess as a okay, so I mean, I'm just sort of curious from a numerical. I see a comment on our live stream here, which has words in it that I don't know, but asking simpler question in gravitational collapse to Schwarzschild, which is interesting from the hypergraph point of view, that of Choptwix scalings.
This is Jose's research area.
Okay.
Yes.
Can you understand the universality of collapse from hypergraphs? Can somebody unpack that question?
I think Jose should probably.
I wouldn't know. I mean, it would be a matter of doing the experiments, and the typical game here is to fine tune the initial conditions so that you get closer and closer to a next singularity. So you are trying to produce the smallest possible black hole, and in the regime in which you are approaching the 0 mass black hole, you see scaling and critical phenomena.
I see. This is the scaling. This is the phenomenon that I think you've told me about before, Jose, about the construction of a naked singularity.
Mm-hmm. Yeah.
So I will say one thing, and so I am not including the data in this paper because it's already sort of beyond it's beyond the scope. But I have actually looked at the Choptuic scalar field bubble collapse problem to try, because I mean, you know, these are referred to as relativistic critical phenomena, right?
Mm-hmm.
And the reason is because of a bunch of analogies with you know critical phenomena in condensed matter physics. The interesting thing that I saw in the hypergraph case is that it's actually not really an analogy, right? That the things you get in condensed matter systems to do with ergodicity breaking become literally breaking of the weak ergodicity hypothesis for the hypergraph evolution. So it's sort of there's a possibility there that you can give some quite qualitative explanation of why you get the ringing behavior in things like the Choptuic solution, in terms of something that's not just analogous but actually sort of mathematically equivalent.
So what you mean is that normally in the hypergraph, it's kind of flapping around, you know, intrinsically randomly, so to speak. And what you're saying is that in these cases where you're trying to sort of titrate down to a tiny black hole, that you end up with something where, just like in the case when you get to a singularity, the thing is definitely not ergodic anymore. The evolution is definitely not ergodic when it's stopped. And so what you're saying is there's another case, there's a different situation in which the evolution becomes non-ergodic.
Right, and okay, so just qualitatively in terms of what that means, I mean, so one way you can characterize weak ergodicity for a hypergraph system in general is you say, okay, well, as I said earlier, you know, the place where we apply these refinement or coarsening, the hypergraph rewriting rules is determined based on, you know, gauge conditions and things that we impose on the metric. So in general, the question is, if you knew that a rule just got applied over here, can you predict where the next rule is going to be applied? And if it's weakly ergodic, the answer should be, well, you know, it's sort of computationally irreducible.
Yep.
But the interesting thing with the Choptuic solution is that as the scalar field bubble reaches approaches its own Schwarzschild radius, the hypergraph rewriting dynamics become progressively more deterministic. So it becomes like there's a much more constrained area in which the hypergraph rewriting rules are being applied, to the point where I suspect in the limit you can actually deterministically predict with fairly minimal computation where the rules are going to be applied.
Yeah, that's
and
really cool.
that would correspond to a breaking of ergodicity.
Well, or more to the point, it's freezing. I mean, the thing froze. And what you're saying is one form of, I mean, space-time froze.
Well, so some regions of space-time will temporarily freeze. Yeah.
Yes. Right. It's which is and frozen in a different way than the freezing, as in there are no more. It's not the case that you get to a singularity where there are simply no more rules to apply. It's something that, you know, it might not be that there are no more rules to apply. It's just that the rules that are being applied in a sort of regular crystal lattice.
It's actually something. It works. Again, this is purely numerical data that I've looked at, so I haven't sort of formalized this at all. But the way I sort of thought about it was that it's almost like the complement of a singularity. A singularity is something where the ergodicity is broken because you can't apply a rule in some place.
Yep.
Whereas for critical phenomena, what seems to happen is you get a situation where the rule has to be applied in a certain place.
Yeah, right. Right, which is what I was saying. I mean, the analogy would be that it is a solid. It's a crystalline solid. Space-time, you know, the concept would be space-time becomes a crystalline solid, right, where as opposed to a gas or a liquid where there's, you know, all sorts of random updates going on.
Right.
So, I mean, go ahead.
Sorry, the standard interpretation of critical phenomena in gravitational collapse is that it's a dynamical system, so it has basins of attractions, each one with an attractor, that's the no-Herr theorem. But the basins of attractions have boundaries, which themselves are dynamical systems, because once you are on the boundary, you cannot leave it. And so the boundary itself has an attractor with codimension 1. There is one unstable mode, the one that would take you to the true attractors. Mm-hmm. And so you do fine-tuning to kill that mode and to stay as close as possible to the boundary. And so as long as you stay in the boundary, you get close to the attractor in the boundary. And
so you're basically saying there's a crater, and there's a bottom of the crater which you would normally go to by virtue of some kind of, you know, gradient descent type thing. but you are somehow keeping yourself circulating around the rim of the crater.
Exactly. And that rim has its own attractor. And so if you manage to stay close enough to the rim for a long time, then you will reach the attractor. And that attractor is the new singularity that Choptic found, the naked singularity. So it doesn't have to be a singularity. It just happens to be a singular solution. It could have been a solution which is not singular. But the important thing is that this is a method to find new, almost stable solutions.
Right. I don't think that's inconsistent with what Jonathan is saying in terms of, I mean, in this interpretation of the crystallization of space-time.
But well, ergodicity, I don't think ergodicity play a role here. It's a matter of finding a very, very particular point in phase space, not a matter of going through the whole phase space, if I understand.
Right, but the failure of ergodicity, by saying you are circulating on the rim, that's saying you don't go visit other places that would be the ergodic thing to do. I mean, the ergodic thing to do is you wander randomly. I really like this concept of this possibility that, you know, which you could see in the causal graph, presumably, of the formation of a crystal, basically.
Yeah, I mean, Jose is right. Like, it's still a bit mysterious what exactly the connection is between ergodicity breaking and the self-similarity in phase space that you see for standard conventional ergodicity breaking or relativistic critical phenomena stuff. Sorry, I'm distracted. I'm trying to pull up some pictures if I can of the Choptic solution, if I can find them.
Unfortunately, I have to go, and I'm about to jump into an utterly different.
But yeah, I mean, this is not a very good picture. But this is a place where you start this sort of regularity that you see in the causal graph is the first. I mean, this is a low resolution simulation, but is the first indication that you get of this is as you're approaching criticality, as you're approaching the critical radius for the Choptic solution.
Right. Just imagine if that was bigger and it was just going back and forth, just like a crystalline solid. Just my comment. I mean, if you imagine, and maybe it's wrong analogy, but I seems interesting to me. This is great. It's really great. I think, yeah, that to be continued. I see Michael on a live stream asking, when will this be released?
It's all available. It's all on GitHub. As Scott mentioned, I think right at the beginning, I'm in the process of documenting and releasing these functions also on WFR. So right now, metric tensor, Ricci tensor are documented. A bunch of others are about to be released on WFR. But if you want to use all of this, I'm just running this directly from the GitHub repository. So if you want to run this, you can do that.
That's you should save this file. This was a good demo.
Oh, right, yes.
All right, I should run along here, but let's I feel like we didn't, there was nothing obvious to me where it was like, oh, that's an obvious design mistake. But I would like to, now that I understand a little bit more what's going on, I'd like to dig in some more. And in addition to design, let's see if we can figure out what dark matter is. That would be a little, in addition to the software design, why not solve a physics problem while we're at it? I think sounds to me like some astrophysics input is needed there, and maybe we can arrange to get some of that. I mean, just like just phenomenological facts that I don't know, for example. All right. Well, this is quite wonderful, and yeah, exciting. And now I need to go read your paper about axiomatic quantum field theory as well, which I keep on being deflected by AIs of various kinds. All right, sounds good. All right, we should wrap up here. Thanks a lot, Jonathan. This is great. So thanks to folks on the live stream. See you all soon.
Yes.